Assalamu alaikum, my dear students. Hope you will be fine and okay. I welcome you all into my today lecture. Today is our lecture number 24, unit 13, and this is the electromagnetic induction. Right. Our today topics include motional EMF, self-induced EMF, and self-inductance, and then the motional EMF. Right. So this is what we will explain in our today class. So let me start with the name of Allah Almighty. Our that is the first topic is the motional EMF. If you remember in the previous lecture, I talked to you about the dynamic and the static types of the EMF. So here it is one of the example of the dynamic EMF, dynamic EMF. And if you remember there, I told that in dynamic, that is the motion of what? The motion of the conductor. The EMF caused by the motion of conductor, the motion of the conductor through uniform magnetic field, through uniform magnetic field, magnetic field. So this is one of the example of the uniform magnetic field. The motion of the conductor through the uniform magnetic field, and it will produce the induced EMF. So first, let me explain this to you. Let me tell you that the induced EMF produced due to the motional EMF is the equal to the product of the magnitude of the velocity of the conductor, the magnetic induction, and the length of the conductor L. And the length of what? And the length of the conductor L. Or it is simply BL. You just remember VBL. And so that is the magnitude of the required induced EMF through this process. So I will explain now how we would like to derive this equation. Clear? Now you see, look at this diagram here, that the you see we have the conducting rails P, Q, the conducting rails P, Q, R, S, as you see. These are fixed, and to the ends of these conducting rail there is attached what? There is attached the galvanometer, which will indicate the presence of the current. Now you see that there is a conducting rod, the conducting rod of length AB. This is a conducting rod, as you see here. It is placed on the conducting rail so that the conducting rod, which has length, the length of the conducting rod is L, and this conducting rod is what? Movable. It can slide freely along the rails of the conductors, which are fixed. Now let's see that to explain this process, the first what we actually do here, that we there is the magnetic field. You see here the magnetic field, this one, the magnetic field, which is into the plane of the paper, right? This means that into the paper, I already told you. So it is in the downward direction, you may say, into the paper. Now let us see that how this thing happens. Once when you move the conductor towards, that is the direction of the motion of the conductor is, as you see, is this one, the velocity of the conductor. Look, this is what the direction of the motion of the conductor is. So if you drag the conductor towards left, right, that is on the side of the galvanometer, then you see that the galvanometer will indicate you current either this way or this way. Okay, right now we are not interested in the direction of the induced EMF, because I already told you that it is very easy to apply the Lenz law or to apply the Fleming right hand rule. So we will do that too. Now you see, look, first of all, let us just see the mechanism here. Now, when you move the conductor across the magnetic field, then you see, look at this loop of the conductor, which I will label as like this. For example, from the point A, as you see here, what is going to happen? This is what the complete loop of the conductor. Okay. So when you move the conductor towards the galvanometer, then the flux changes. Why the flux changes? Because it is because of the fact that, for example, if this is the new position of the conductor, let's say if your conductor arrive at this point, for example, before it was a distance x1, now it is at a distance x2, let's say. So what is going to happen, that the area changes, and I told you that whenever there is the change in area or the change in magnetic field, so here we have the change in area. So what happens here, that there is a changing magnetic flux, and that changing magnetic flux would cause the induced EMF within the circuit. Now, since the magnetic field is uniform, and now let's see, as I told you, that look at the path of the current through the loop. I will just mark it like this, as you see, through this one conductor like this, for your simplicity. Let's see, I may do it with this one. Okay. So you see here, look, the current through the conductor will be passing through the galvanometer like this. Okay. Now see here that what is going to happen here. Look, if there is a charge particle, let we have electron, the free electron inside the conductor. Now what is going to happen, that if you move, there is induced current. Now according to the Fleming left hand rule, that if you apply the Fleming right hand rule, so you see that that is the magnet, that is the thumb will point in the direction of motion, and the first finger will point in the direction of the field, like this one, as you see. For example, according to this diagram, look, if you apply the right hand rule, like this, if you see, look, if this is the thumb, so the thumb will point in the direction of force thumb. You do it at your home. The first finger will point in the direction of what? The direction of the magnetic field be. This is the direction of the velocity. Okay. Because you will apply in an external force, and you can see it right here. This is what? This is the direction of the external force which you apply to keep the conductor moving. So we indicated it with the velocity, right? The velocity is in that direction. Clear? And this will be the direction of what? This will be the direction of the current I. So for the positive charge particle, if the charge particle is positive, this is for the conventional current direction, positive charge particle. But you know, in for the electron, this is for the electron. But you know that we usually consider what? We usually consider inside the conductor, we consider the conventional current direction. What we consider? the conventional current direction, conventional current direction, current and direction. So according to the Fleming left hand, according to the Fleming right hand rule here, definitely that if there is a charged particle like this one, and if we apply the conventional current direction, then for a kind of positive charge, what will happen? That there will be what? That it will move in the direction from A to B, right? It will move in the direction from what? A to B. So definitely that a positive charge always moves in the direction of the electric field intensity. So we are getting the kind of feeling is that this X is the positive terminal of the battery, and this will then X is the negative terminal of the battery. So the current rises from the point A and to go to the point B. So the desired current direction will be this one, which is already indicated like this. So the current will then begins to flow in this direction as you see, right? And that is of course anti-clockwise direction. So that will be our direction. Now you know that, look, whenever there is a current carrying conductor, so that is from the current carrying conductor, look what happens, that this is the current carrying conductor I, then there will be a magnetic field. Since this is induced current, so there will be induced magnetic field also. And what will be the direction of the induced magnetic field? This will be the direction of that induced magnetic field. So it will give you the kind of feeling, because you know this is now, because there is already one permanent magnetic field B. So you know that now this is just like when a charged particle in current carrying, that is a charged particle inside uniform magnetic field or current carrying conductor in a magnetic field, and it will experience a force, and that force which it experience will be Fm, and it is in the direction opposite to that of the external applied force, right? And so the charged particle will have two forces acting on it. The electrostatic force on the charged particle is in this direction, the F electrostatic force. And this is what? This is the F electrostatic force on the charged particle. Clear? Now for this one, since there is what? Now if we apply the Fleming left hand rule, then according to the Fleming left hand rule, that the force on current carrying conductor inside the uniform magnetic field. So you see that, look, the direction of the current is in, that is the field is in the downward direction, and the current is in the upward direction. So definitely this will be the magnetic force that acts on the charged particle in the opposite direction. And this force will tries to slow down the electron. It will what? It will tries to slow down what? To slow down the conductor across, moving across the magnetic field. In that is in the light of what? Law of conservation of what? The law of conservation of energy. So look for this charged particle. In order to move the charged particle with uniform speed, then there must be what? That the electrostatic force must be in balance to the magnetic force. Now as we know that, look, now let us see to derive this relationship. As we know that when force acts on the charged particle, then the applied force is doing work done against what? Against that magnetic force, right? This is your applied force or F external force, and that is a magnetic force. So you are definitely doing work done. So from the from the rate of doing work done, from the rate of what? Rate of doing work done, doing work done. From this rate of doing work done, what we can write, that work done is equal to what? This work done will be equal to the that is the, rather what I would say, the power, which is equal to F dot V. So here the force with you, the external force required to keep the conductor moving will be equal to the magnetic force acting on the conductor. And that force is equal to what? It is equal to Bell into, that is what? Bell, where L is the length of the conductor, I is the induced current, and B is the magnetic field strength, N to the velocity of the conductor, F dot V. So that is the rate of doing work done, or the power delivered to the circuit, is BLV. So this is one equation, right? But this work done, since you know that energy is neither created nor destroyed, so this work done will appear in the form of electrical energy, right? Yeah, we can say that the rate, that is the in the form of electrical energy, and the rate at which this mechanical energy changes into electrical energy, then we will be writing the rate of electrical energy, the rate of production of electrical energy. Yeah, the rate of production of electrical energy. Yeah, very simply, I would like to tell you that it is actually what? The rate at which electrical energy changes into magnetic, sorry, electrical energy, oh my God, non-electrical, the rate at which non-electrical energy changes into electrical energy. Now, what we will, how we will do it now, that this will equal this rate. It is always equal to the product of what? It will be the product of the induced EMF that is produced here, and the product of the induced EMF and the induced current in the circuit. Number two. So from 1 and 2, this is so easy. From 1 and 2, we can write that induced EMF equal, that is the induced EMF, since energy is neither created nor destroyed, so power N, this is in fact power N, and this will be our what? Power out. So the power N for frictionless system, it must equal power out. So yeah, the power out will equal power N. So this will be equal to the Bell phi. And what does this means? That induced EMF equal to B I V, right? That is the required induced EMF, where the B, not BIV, BLV. This is BLV. Okay, so because I and I get cancelled, this and this get cancelled. So this is what? This is the required relation for the induced EMF caused or produced by the emotional EMF. Our next topic is the self-induced EMF and self-inductance. The self-induced EMF and what? And the self-inductance. So let us do this. The self-induced EMF. What? The self-induced EMF. Self-induced EMF and the self-inductance. I will come to the self-inductance later on. What is the self-induced EMF? If you remember, I told you that whenever there is changing magnetic field, that changing magnetic field, changing B, always what? Always produce induced EMF. So here we are using that effect. So self-induced EMF is the process of process of generating induced current, yeah, induced EMF due to the change of current, due to the change of current, within the circuit itself, within the circuit itself, This is known as the self-induced EMF. Mathematically, the self-induced EMF is equal to L into delta I by delta T, where what is this L? This is the self-induced EMF. This L is called the self-inductance, and I will explain later on what is this self-inductance. And this factor here which you see is the change in current with time, changing current. Now, which phenomena this process use is the changing current may produce changing magnetic field, and it will cause or it will produce the induced EMF. Now let us start how. Let me derive this relation for you, derivation. Now let us see here that if we have what? We have the solenoid, as you see, and this solenoid has length L, right, and it has the number of turns per unit length is N by L. Here we supply, rather best to supply the AC current. Why? Because AC is changing magnetic, what? It is a changing alternating current. We have the source which is both which vary both in polarity as well as in magnitude. Now you know that whenever there is a current flowing through the solenoid, there is a magnetic field. This for the direct current or for a steady current, this is constant. The magnetic field strength does not change. But you know that when either it is switched on or when it is switched off, there will be induced EMF. Why? Because when you, for example, when you switch it on in the beginning, the current will build from 0 to certain maximum value. During this process, the current increases. So the magnetic field changes and there is changing magnetic field. Then some of the magnetic field lines will pass from the coil within itself, and it will cause induced EMF within a circuit in a direction opposite to that of the primary current in the circuit. Here one thing is important. We have two kinds of current. One, the primary current. This primary current caused by source, and one we have the induced current, and the induced current caused by the changing magnetic field due to the changing current. One, we have the induced current. The induced current, if this is the primary current, then the induced current will be in the direction opposite to what? The induced current will be in the direction opposite to that of the primary current, like this one. So the two current are opposing each other when you switched on. But when you switch off, then the two current will be in the same direction. So there will be a greater induced EMF than if you switch it off. Why? Because the direction of the, if you switch it up, the changing magnetic flux, what happens? It decreases, right? Why? Because the current falls and there is induced EMF, but this time the induced EMF will be in the direction of the primary current, right? So here, if you just look to this diagram here, that what is here right now, this is what the intricate detail, right? With this includes its minute detail with its loop, the loop 1, loop 2, and the magnetic field caused by it, and the magnetic field due to the current, due to the induced current. Here what you see, look, that when the magnetic field changes, then in this case here, what you see, there is induced current, and that induced current is opposite to the primary current, right? That is the, it is the magnetic field due to the primary current, and when that primary current change, the magnetic field changes. There is a changing magnetic flux, and some of the field lines pass from this solenoid from on coil, okay, and it will generate induced current, right? That is the induced current, and you see they have the opposing effect, right? Now experiment shows that, experiment shows that experiments show that the, we already know that the changing magnetic flux in the coil, the changing magnetic flux is directly proportional to the change of current in the coil. So the faster the change of current in this coil, look, that is the change of current, the greater the change of current, the greater will be the flux change. Now this can be even increased further if there are more number of turns, right? For the greater number of turns, the flux will multiply by that number of turns. So this is directly proportional to the changing current. What then we can write that this N delta pi equals to a constant and to the changing current I. This constant is equal, this constant is called inductance. We call this what? The self-inductance of the coil. This is called what? This is the called the self-inductance of the coil. Self-inductance of the coil. The self-inductance of the coil. And this I label as equation number 1. And this self-inductance of the coil can be written as N delta pi by delta I, right? This is a very important equation, and throughout this book, it will not leave you alone. So better you remember it in a very short form, N pi equals Li. It is usually most often used equation. Now you see that this constant of proportion is self-inductance. It depends on the number of turns on the in the coil. Number of what? The number of turns in the coil. It depends on the area of cross section of the coil, area of the number of turns per unit length. Okay, a number of turns per unit length, area of cross section of the coil, right? And the nature of the core material. Nature of what? The nature of the core material. And if this self-inductance is equal mu naught times N square L into A, right? So this NA actually the number of turns per unit length. So we, as I told you, N number of turns per unit length. Clear? So if you just apply this, then you can solve for this. Now you see, look, that it all depends the area of cross section, the number of turns per unit length, and the core material. This is what the core material, the permittivity of the core material. For example, whether there is free space, if the free space is replaced by the iron bar or the iron rod, the ferromagnetic substances, then the self-inductance increases and the induced EMF will in turn increase, right? So these are usually what sometime I call, but rather these are totally geometric, depends on the geometry, yeah, geometric factors, because it depends on what, on the geometry of the solenoid, because area of cross section, length, it is the geometry. What is inside are the core material. It is nothing but it is geometry of the coil. So it depends on all these factors. Now, but from Faraday law, as we have bits studied earlier, but from Faraday law, Faraday law, what the Faraday law states, that the induced EMF is equal to minus delta pi by delta t, the rate of change of magnetic flux, right? This implies here that the E delta psi into E psi delta t equals minus n into psi, not psi, it is pi, right? Or we can say that n, this implies that n delta pi equals minus induced EMF into delta t. This is equation number 2. So now from equation 1 and 2, from 1 and 2, what I can write, that this minus E psi by delta t equals, it equals L delta I, right? And this L delta I, this implies that induced EMF is equal to minus L delta I by delta t. Here the negative sign indicates direction, indicates the direction of the induced EMF, direction of the induced EMF. It indicates what? The direction of the induced EMF, and can be found by using Lenz's law. Lenz's law here. L is known as the mutual inductance, and this L can be written as like this, delta I by delta t, right? And what is this delta I by delta t? This delta I by delta t is rate of change of current, rate of change of current, right? Now, what is the SI unit? The SI unit of this self-inductance, which is called self-inductance, the SI unit is what? The SI unit is Henry. It is what? It is Henry. And 1 Henry equal to what? It is, what is the unit? This volt, the unit of current sense, because if you see, we can write it like this, delta t into by delta I, that is second, and the unit of current is ampere, so per ampere. So a self-inductance of the conductor is said to be 1 Henry if there produces 1 volt of induced EMF when the current changes through the solenoid or inductor is at the rate of 1 ampere per second, right? Then we say that the inductance is 1 Henry. Now, greater the inductance, greater will be the induced EMF, which is more visible here. Now remember that the self-inductance, this does not depends either on the induced EMF or on the rate of change of current. It only depends on the geometric properties of the conductor. Depends on what? Purely depends on the geometric properties of the conductor. Geometric properties of the conductor, such as number of turns per unit length, right? Area of cross section of the coil and of the core, nature of the core material, permittivity, which I explained to you in the previous chapter. So this is all for today. So good luck. Thank you very much. Inshallah, see you in the next lecture, which will be the mutual inductance, and these are very important topics.